Hi, my name is Katie Wong, and I'll be covering my motion of a falling object lab. The purpose of this lab is to measure an object's motion after it is dropped from rest at some height. At the end of the lab, I could compare my observed data with two computational models. The computational model that took into account both gravity and drag was more similar to my observed results than the computational model that only took gravity into account. One principle we use is Newton's second law, which states that the acceleration of an object is dependent on the net force acting upon the object and the mass of the object. Newton's second law also includes the momentum principle, which can be used to derive the velocity and position update formulas. We use Newton's second law here because we need to find the net force acting on an object by summing its forces from interactions with other objects. Later from the experiment, we will also see that the object is affected by a non-zero acceleration, which relates to the momentum principle. Another principle we use is the formula for gravitational force, which you see here. Since our object is falling towards the ground, we know it is affected by gravity. Finally, we also use the formula for drag force, which is an opposing force to the gravitational force, which results when the solid object interacts with the fluid air. The greater the surface area of an object, the greater the drag force. We know that drag force is affecting the object in the experiment as our object falls somewhat slowly. For my video, my system is the paper ball, which is my object, and the surroundings is the earth and its air. I positioned my coordinate plane with the positive y-axis going up and the positive x-axis going right. So my object moved along the negative y-axis. I used my ruler as the scale calibration. My initial conditions are shown here. You can see the y-graph is exponentially moving in the negative direction due to the acceleration of gravity on the object. For the computational model that only took into account the force of gravity, I plugged in the initial conditions I mentioned in the previous slide and had the proportionality constant set to 0. The net force will only be the force of gravity, as you can see in line 70. Then, using the velocity update formula, I calculate the ball's final velocity and use that to calculate the ball's final position in the position update formula. For the computational model that took into account the force of gravity and drag, I have almost the same code as the previous slide. Some changes are the proportionality constant, which I found by trying different numbers until the endpoint of the model was about the same as my observed data. Also, I have the formula for drag force here, which is combined with the force of gravity to find net force. Here's the data from the two computational models and the observed data on one graph. Notice how the computational model that included drag more closely models what we see in the real world. However, the middle of the graph does have some discrepancy. This could be because of human error when positioning the center of the paper ball and tracker, as the ball was blurry during some frames. It could also be from how I did this experiment a little bit too close to the AC unit, which was blowing wind. And it could also be from how the ball could have been slightly turning as it fell, which would mean that its B value in the drag force formula was not constant like I had assumed because the paper ball is not completely smooth. Also, notice how the gravity-only model displays the object at a much further position compared to the models that include the drag force at the same time points. Remember that this is because drag is opposing gravity, so the object's net force in real life going downwards is smaller and it is falling at a slower rate, so it does not move as far in the same amount of time. For our what does it mean question, we can see that the model that considers gravity and drag will reach a terminal velocity. This is because it looks like towards the end, the velocity becomes constant, which indicates zero acceleration and zero net force. Remember that we have zero net force here because the force of gravity and drag are equal to each other. For our what if question, the object's terminal velocity is still the same if it had an initial negative velocity in the y direction. The only difference here is that terminal velocity is reached more quickly compared to if the ball is dropped from rest. So to conclude, in this lab we used Newton's second law, the gravitational force, and the drag force to model the motion of an object. We recorded and analyzed vertical motion of a paper ball and tracker and compared data to the GlowScript computational model, and we noticed that in the real world, drag is present along with gravity.